Good morning, students. Myself, Dr. Intes Karta, Associate Professor, Department of Information Technology. Today, we begin the course Fundamentals of Artificial Intelligence, which is a minor course designed for S6 students to give you a strong foundation in AI concepts, irrespective of your core branch. We will first discuss the course outcomes. There are 5 course outcomes. The first one is understanding AI history, foundation, and scope. So understand how artificial intelligence evolved from early ideas to modern systems. We will discuss the foundations of AI, understand the scope of AI in real world applications, and these outcomes help the students develop a clear conceptual background of what AI can and cannot do. Second course outcome is applying search algorithms for problem solving. Students will be able to understand different types of search techniques used in AI. We will discuss the use of suitable algorithms to solve classical AI problems. This outcome focuses on developing logical thinking and problem solving skills. And the third course outcome is knowledge representation, inference, and reasoning. So students will be able to understand how knowledge is represented inside an AI system. And we will discuss different methods like proposition logic, predicate logic, and understand inference mechanism to derive a new knowledge and analyze how AI system reason and make decisions. And this outcome explains how a machine store information or knowledge and draw conclusion like human. And the fourth course outcome is AI planning techniques and algorithms. So students will be able to understand the concepts of planning in AI, analyze classical planning techniques, understand hierarchical planning approaches, and learn how AI system plan a sequence of actions to achieve the goal. So this outcome helps the students to understand decision making and goal oriented behavior in AI. And the fifth course outcome is learning techniques and intelligence system. Students will be able to understand different machine learning techniques, including decision trees, explanation based learning, reinforcement learning, and also gain basic knowledge of expert system and genetic algorithm. So students will be able to analyze how AI system learn from data and experience. So this outcome introduces students to how machines improve performance over time. Next, we will discuss about textbooks. So here we are following two textbooks. The first one is Stuart J. Russell and Peter Norvin's Artificial Intelligence, a Modern Approach. That is the first textbook we are following. And the second one is Elaine Rich and Kevin Knight, Artificial Intelligence. These are the two textbooks we are following. And this is our week one topics, concepts of AI, history, overview of AI application areas, intelligent agents, and structure of agents. We can see the definition of AI. Artificial intelligence is a wide-ranging branch of computer science concerned with building smart machines capable of performing tasks that typically require human intelligence. Here we can see the word building smart machines. What is smart machines? So smart machines that can learn, decide, and predict. So for example, face unlock on phones, Google Maps suggesting routes, Netflix representation, smart detection in email. So according to the father of artificial intelligence, John McCarthy, he actually coined the term artificial intelligence in 1956. That's why he is called the father of AI. According to his words, artificial intelligence is the science and engineering of making intelligent machines, especially intelligent computer programs. That means intelligent behavior shown by machines using computer programs. So there are 4 approaches to define AI. These definitions are grouped into 4 categories based on the 2 questions. There are 2 questions. The first one is, should machines think or act? That is the first question. And the second one is, Should they behave like human or rationally? These are the two questions. We will see the definitions. The definitions on the top are concerned with thought process and reasoning, whereas the one on the bottom addresses behavior. The definition on the left measure success in terms of fidelity to human performance, whereas the one on the right measure against on ideal performance measure called rationally. We will see one by one. The first one is thinking humanly. Thinking humanly means make machines think like humans think. Here the goal is to copy the human thought process. So this approach focuses on simulating human thought process, how the human thinks. The same way we have to make the machine that machine should think. It tries to understand how human reason, learn, remember, and solve problems. So knowledge from psychology, neuroscience, and cognitive science are used here. The goal is to model the internal mental process of the human. For example, we can say that a program that solves programs step by step like a human. So here we have to simulate human memory, perception, and learning. Next one is think rationally, thinking rationally, making machines that think logically and correctly. So this approach is based on logic and mathematics. So it uses formal logic, that means proposition logic and predicate logic, that we will discuss it later. The goal is to derive correct conclusion from the given facts. So there are some facts are given, and from the facts we have to derive the correct conclusion. For example, expert system, automated theorem provers, logic-based AI system are the examples. And the next one is acting humanly. That is a Turing test approach. Acting humanly refers to creating machines that behave like human. So the Turing test that is actually introduced by Alan Turing. So if according to this Turing test, if a machine can imitate human behavior such that human cannot distinguish it from another human, it is considered intelligent. That is a Turing test. That means if a machine can imitate human behavior such that the human cannot distinguish it from another human, it is considered intelligent. Focus is on observer behavior, not internal reasoning. For example, we can say that chatbot, virtual assistant, humanoid robots are the examples. And next one is acting rationally. That is rational agent approach. Acting rationally means designing agents that take the best possible action to achieve a goal. This approach is based on the concept of rational agent. So rational agent means that perceives its environment using sensors. That means it collects information from the environment using the sensors and act using actuators and chooses the action that maximizes the performance measure. It does not try to imitate human but focus on optimal behavior. That is acting rationally. So for example, we can say that self-driving car, chess playing programs, autonomous robots, intelligent recommendation systems. So we can say that acting rationally is the most widely accepted definition of AI today. Next, we will discuss the history of AI. We will start from foundations before 1950. That period we can call it as pre-AI era. In the year 1943, Warren M. McLoach and Walter Pitts proposed a model of artificial neurons. The human brain consists of neurons, and this McLoach and Pitts showed that a neuron can be modeled using logic and mathematics. So a neuron can perform basic operations like a and or not operations. means logical operations. This proved that thinking can be represented computationally. In the year 1949, Donald Hebb demonstrated an updating rule for modifying the connection strength between neurons. It is called Hebbian learning. So according to the Hebbian learning, neurons that fire together wire together. That means if two neurons are activated at the same time, the connection between them becomes stronger. So this explains learning through experience. For example, when you repeatedly practicing a skill, the brain strengthens certain neural connections. Similarly, AI system can learn by adjusting weights. So the Alan Turing asked the famous question, can machine think? He proposed the Turing test to measure the machine intelligence. In 1950, he proposed this Turing test. Can machine think? Next is birth of artificial intelligence, 1955 to 1956. In the year 1955, this period actually marks the official beginning of artificial intelligence as a scientific and academic discipline. During this year, AI moved from theoretical idea to the actual working programs, and the term artificial intelligence was formally introduced. In the year 1955, Alan Newell and Herbert S. Simon created the first artificial intelligence program, which was named as Logic Theorist. This program had proved 38 out of 52 mathematical theorems and finally new and more elegant proofs for some theorems. So the logic theorist was designed to mimic human problem solving skill. It focused on proving mathematical theorems automatically. The logic theorist is considered the first AI program. So John McCarthy officially coined the term artificial intelligence in the year 1956 in a Dartmouth conference that is considered as the birthplace of AI. AI was recognized as a separate academic field for the first time. Next is the period 1952 to 1969. So this period is known as early enthusiasm, great expectations phase of artificial intelligence. During this time, AI researchers achieved several impressive but limited successes. So before 1950, computers could only calculate numbers. So during this period, AI showed small intelligent behavior. So according to John McCarthy, Lukma no hands. That means AI shows small intelligent behavior. We have already seen the first AI program, that is Logic Theorist, that is developed in 1956, that proved math theorems. Next is General Problem Solver, that is developed by Newell and Simon, that is based on physical symbol system hypothesis. So GPS, the main idea is break the problems into sub-goals. So that means solve one sub-goal at a time, similar to human thinking. So according to Newell and Simon, any system that shows intelligence works by manipulating symbols. Symbols means something that represent something else. For example, we can say that numbers, words, images, and data. So any system that shows intelligence works by manipulating these. The next is checkers. That is, AI learns to play games. Program learned from this checkers program that is developed by Arthur Samuel. He wrote a program to play checkers. So the program learned from experience, improved by playing itself, and also eventually beat its creator. So this proved computers can learn, not just follow the rules. In 1958, John McCarthy created Lisp, a programming language specially for AI. So Lisp was the most important AI language for 30 years. Then McCarthy proposed something called advice taker. Advice taker, that is the foundation of AI system. Think of it as an intelligent assistant. So according to McCarthy, the advice taker means we can consider the system as an intelligent assistant. It could store knowledge, reason using logic, and accept new information and plan actions. For example, we can say that airport, if you tell to the machine, airport is far, then it can plan to go by car. Many modern AI ideas came from this concept. To make AI easier, researchers actually created microworlds, that is a limited environment. So microworlds are small and controlled environment. So solving calculus, solving word problems, IQ style puzzles. So these programs looked intelligent, but only inside within a small world, that is micro world. The most famous micro world was block world. So blocks world means blocks on a table. There is a blocks on a table, a robotic hand is there, and English commands. The robot hand can pick one block at a time and move it and place it somewhere else. Then next is SHRDLU, that is developed in 1972. It is actually Natural Language Understanding Program. Then early neural networks. Some researchers said instead of logic, let us copy the brain. So they developed perceptron. So these models could learn patterns. So this is the starting point of today's deep learning. All these systems worked well only in small environments. So they failed in real world, complex situations, common sense reason. So this lead to disappointment, which later caused the AI winter. Next period is 1966 to 1973. Now we are going to see a phase where AI researchers were forced to face reality. A dose of reality means AI researchers realized that intelligence is much harder than they initially thought. Early AI worked well only in simple problems. When they tried real world problems, system failed. So according to Herbert Simon, there are now machines that think, learn and create, and very soon their abilities will match the human mind. But these predictions did come true, but not in 10 years. They took nearly 40 years. So the major problem was no real understanding. The most early AI programs did not understand their subject. They used syntactic manipulation, that means manipulating symbols, following rules, and then without understanding the meaning. So that means without understanding meaning, what we have written, just follow the rules. So the machine translation failure. So the computer translated word by word, but it had no background knowledge, no understanding of meaning. That is, this really failed in real language. In 1966, a government committee evaluated machine translation. They concluded no successful general machine translation exists. So as a result of this, all US government funding was stopped. This is ALPSC report. So this was a major shock to AI research. Most AI problems actually use search. Search means they tried one solution, then another, then another. So this actually worked in micro worlds, that means small environment. But real world problems have millions of possibilities. So this leads to something called computational complexity. That was the second major problem, that is computational complexity. Then early AI also tried machine evolution, now called genetic algorithms. The idea was make small random changes, keep useful changes. In theory, it sounded perfect, but in practice, thousands of CPU hours is needed, and almost there is no useful result found. It is because of computers were too weak at that time and representations were poor. In 1973, the Lighthill report criticized AI research in UK. The report said AI cannot scale to real-world problems due to combinatorial explosion. As a result, the British government stopped AI funding except in two universities. This further slowed AI research. The third major problem is limits of perceptron. But interestingly, the backpropagation was discovered in 1969, but it was ignored at that time. It became popular only in the 1980s. Next period is 1969 to 1979, knowledge-based systems. So in the first decades of AI, that means 1950s to 1960s, problem solving looked like just use general purpose search. Break the problem into small reasoning steps. Try all possible combinations. These approaches are called weak methods. They do not scale to complex real world problems. That means there is no domain knowledge. So it works only for small problems. Then from 1969 to 1979, AI researchers changed their thinking. To solve hard problems, you must almost know the answer already. So that means use domain specific knowledge and take larger reasoning steps. And also they focused on narrow expertise. Next, we will see the expert systems. The first knowledge-based expert system was Dendral, that was used to identify the molecular structure of a chemical component. The input was chemical formula and mass spectrometer data. And this followed McCarthy's advice taker idea that we have already seen. It was considered as the first successful knowledge intensive AI system. Initially, the program tried generate all possible molecular structures and predict the spectrum of each and then compare with the real, but completely impractical. That means there are too many possibilities are there. So they discussed with the expert chemist. So chemist said, we don't try everything. We look for patterns in the spectrum. Then patterns indicate non-substructures. So once a substructure is known, the number of possible molecules reduces dramatically. Then next was MySyn. The MySyn is a medical expert system that diagnosed blood infections. It used about 450 rules and it worked better than junior doctors. MySyn actually used certainty factors. So we know medical decisions are uncertain. So MySyn handled this using certainty factors. For example, we can say that if symptom is X, then there is a possibility of 0.7 uh, that the disease is Y. If we have a symptom X, we cannot say that this symptom is for a particular disease. There is a possibility of many diseases actually. Next is AI becomes an industry from 1980 onwards. From the 1980s onwards, something major happened. AI moved from laboratories to companies. That means till 1970s, artificial intelligence was mainly a research topic in universities. From the 1980s, AI moved out of labs and entered companies. The first major success was that proved AI can make money was the expert system called R1. R1 system. Early AI program solved toy problems. So R1 solved a real industrial problem that was used in digital equipment corporation and that saved $40 million per year. And this actually increased trust in AI system. So this made the companies realize AI is useful and profitable. So after R1, many companies started AI departments. Not only in companies, even government invested in AI. The most famous was Japan's project. So Japan announced a 10-year plan to build intelligent computers. They plan to use logic programming, prolonged language. So that is a fifth generation project in 1981. Then US started a project MCC, then UK ALVI program. So AI market grew from millions to billions of dollars. When companies failed to deliver promises, funding stopped. This period is called a AI winter. Next is from 1986 onwards. We already know that neural network existed earlier, but they failed in 1960s because they couldn't learn complex patterns. But in the middle 1980s, neural network came back strongly. The key reason for this is the backpropagation learning algorithm. And this was first discovered in 1969 by Bryson and Ho, and it became popular only in 1980s. So we know that earlier neural networks had only one layer. So the backpropagation allowed multiple hidden layers, error correction, learning complex patterns. So that is why neural networks suddenly become powerful. And in 1986, Rumelhart and McClelland published a famous book, Parallel Distributed Processing. So this book spread neural network idea worldwide and created huge excitement. So these neural network models were called connectionless models. Symbolic AI focused on rules and symbols, while connectionist AI focused on learning from data. So today we understand that both approaches are important and they are complementary. Next is from 1987 onwards. AI adopts the scientific methods. So earlier AI relied heavily on intuitions and small toy problems. But the late 1980s onwards, AI began to follow the scientific methods. AI early isolated itself from other disciplines. Now it integrates ideas from statistics, optimization, control theory, and information theory, and so on. Modern AI research requires rigorous experiments, statistical analysis, and reproducibility using shared data set. For example, in speech recognition, today hidden Markov models dominate because they are mathematically sound and trained on large data sets. So these models are not models of how humans think. They are engineering solutions that work well in practice. So that means there are hypothesis testing, controlled experiments, statistical analysis, and reproducibility is there. Julia Pearl reintroduced probability into AI through Bayesian network, allowing AI system to reason under uncertainty. Next is from 1995 onwards. From 1995 onwards, AI researchers started focusing on Word Agent, a system that can sense, think, decide, and act continuously in an environment. This phase is called the emergence of intelligent agents. One of the most famous complete agent architecture is SOAR, developed by Alan Newell, John Layard, and Paul Rosenblum. So SOAR attempt to model general human problem solving and learning. The internet became the most important environment for the intelligent agents. So AI systems are everywhere online today. And that's why we commonly hear the term bots, chatbot, web crawlers, and recommendation bots, etc. So sensors means camera, microphones, or sonar do not give a perfect information. Therefore, agents must reason and plan under uncertainty using probability and decision theory. So, self-driving car are a perfect example of intelligent agent. Their success comes from combining sensors, control theory, mapping, localization, and planning. So, traditionally, AI system focused on algorithms, but modern AI shows that more data often matters more than a better algorithm. So, the web provides trillions of words and billions of images. So from 2001 onwards, the availability of uh, very large data sets. So that means Yorosky showed that AI can learn word meanings without labeled data using huge text corporation. And in image processing, performance improved dramatically only after using millions of images. And from 2001 onwards, the web provides trillions of words and billions of images. Biology provides data, and these actually fuel modern AI. So the large data sets and learning algorithms reduces the need of hand-coded knowledge, and this helps overcome the knowledge bottleneck. With widespread real-world application, AI entered a new spring, ending the AI winter. Then from 2011 onwards, Uh, in the year 1997, IBM Deep Blue beats World Chess Champion Gary Kasparov and become the first computer to beat a World Chess Champion. Then in the year 2002, for the first time, AI entered the home in the form of Roomba, a vacuum cleaner. And in the year 2006, AI became in the AM came in the business world. Companies like Facebook, Twitter, Netflix also started using AI. And in the year 2011, IBM's Watson won Jeopardy, a quiz show where it had to solve the complex questions as well as riddles. Watson had proved that it could understand natural language and can also solve tricky questions quickly. In the year 2012, Google has launched an Android app feature, Google Now, which was able to provide information to the user as a prediction. In the year 2014, chatbot Eugene Guzman won a competition. In the year 2018, the project debater from IBM debated on complex topics with the two master debaters and also performed extremely well. Next, we will see AI application areas. Where do you see AI in your daily life? Commonly, Google Maps, Instagram, Alexa, Netflix, ChatGPT, online exams, and fraud alerts. So AI is not one technology, it is applied across many domains. AI application areas are domains where artificial intelligence techniques are used to solve real-world problems. So we will see some of the domains. First one is machine learning and data analytics, where AI system learns patterns from data and make predictions and classifications. So, for example, student performance prediction, loan approval in financial institutions, then recommendation systems, Amazon, Netflix, etc. Next application area is natural language processing, NLP, understanding human language, text and speech. Examples chatbot, customer care as a customer care, then Google Translate, email spam filtering. Next application area is computer vision. Example face recognition, medical image diagnosis, that is X-ray and MRI, then traffic monitoring. Next application area is robotics and intelligent automation that combines AI with the physical machines. For example, industrial robots, autonomous vacuum cleaners, delivery robots, etc. Next is expert systems. So expert system means mimics human expert decision making. Example, medical diagnosis system, fraud detection system, etc. Next is application is healthcare applications. There, this disease prediction is possible, medical image analysis is possible. We already discussed in computer vision, X-ray and MRI we can analyze. Then drug discovery. Next is finance and banking. There we can use AI for fraud detection, credit scoring, and algorithmic trading. Then next application area is smart systems and IoT. Most commonly used AI, that is smart homes, smart cities, energy optimization, etc. Our next topic is agents and environments. What is an agent? An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. So simply we can say that agent is a decision maker. And here we can see the sensors that perceive the environment. So that means it will collect information from the environment. And the agent will decide which action we have to perform. And accordingly, these actions are done through actuators. So for example, we can consider human is an agent. Then eyes, ears will be the sensors and hands, legs will be the actuators. For example, if you are considering robot as an agent, then camera, IR sensors will be the sensors that collect information from the environment and the actions are done using motors. For a self-driving car, there will be camera, GPS as sensors and steering and brakes will be the actuators. If you are considering a chatbot and text input will be the sensors that collect information and text output will be the actuator. So the perceive means what the agent sense at one moment. And here we can see an agent's perceived sequence is the complete history of everything the agent has ever perceived. So that means perceived sequence means memory of all perceptions till now. In general, an agent's choice of action at any given instant can depend on the entire perceived sequence observed to date, but not on anything it hasn't perceived. So that means an agent cannot guess. It only uses what it has sensed. Agents act rationally based only on percepts, not hidden information. And one more thing, what is an environment? Environment is anything outside the agent that it interacts with. So for example, we can say that for a chess program, chessboard is the environment. For a vacuum cleaner, room will be the environment. For a student classroom, so we can say that agent and environment are always considered together. So this is the structure of an agent. Here in this figure, we can see that the sensors that perceive the environment, that means it collects information from the environment using the sensors. And there is a square box we can see, that is the agent program. Accordingly, we will do the decision making process. And then after completing the decision making process, and these actions are done using actuators. And here, this is the explanation for that. Here you can see agent means architecture plus agent program. So sensors that is used to perceive information from the environment. And some examples are given here. And then actuators used to act upon the environment. And the examples are also listed below. Then what is an agent program? So agent program means a set of rules or algorithms that map percepts to actions. So we can say that that implements decision making logic. So in the structure we have seen a square box. So actually that is the agent program. And agent program means there will be a set of rules. And according to that rules, some conditions and rules will be there. And so according to that, the agent will decide what action we have to perform. So agent architecture is the hardware or software platform on which the agent runs. For example, we can say that robot hardware, computer system, virtual environment, etc. Next is agent function. So how does Google Maps decide which route to show you? So behind this decision is something called an agent function. So agent's behavior is described by the agent function that maps any given percept sequence to an action. So we can say that agent function means what the agent should do. That is, according to theory, we can say that what the agent should do is the agent function. And agent program means how it is actually coded. That is a practical way. And one agent function can be implemented by many different programs. So agent function for an artificial agent will be implemented by an agent program. So we can simply say that agent function is an abstract mathematical description and the agent program is a concrete implementation running within some physical system. So these are the functions of an intelligent agent. First one is perception. We already discussed, collect information from the environment using the sensors, and after perceiving the information, it will convert the raw data into a meaningful perception. For example, self-driving car detect road signs using cameras. That is an example. And the agent program has to work on it. So whatever data collected from the environment, that should be converted into a meaningful format. Next function is decision making or reasoning. That means evaluate the percepts to decide the best action. So for that it uses rules, search algorithms, knowledge bases and machine learning models. Using this, it will find the perfect or best action. Next is action. So after finalizing the action, they execute actions through actors that affect the environment to achieve the goals. For example, we can say that robot picks an object. For a self-driving car, applying brake or turn the car to left or right. So all these are actions. Then learning. Another function is learning that improves the performance based on experience and also adapt to changes in the environment. For example, recommendation systems learning user preferences. Next function is goal achievement. So that means whatever action the agent is taking, that should reach to the goal. So works towards achieving specific goal efficiently. So uses performance measure to evaluate the success. We will see what is performance measure in the next coming slides. So we will see the example, vacuum cleaner world. The vacuum agent perceives which square it is in and whether there is dirt in the square, and it can choose to move left, move right, suck up the dirt or do nothing. You can see in the figure, you can see there are two squares A and B and one vacuum agent is there, and what it will do is it will first check where it is and there it is clean or not. So if A is clean, if it is placed for, initially it is placed in square A and it will check whether it is clean or not. If it is clean, then it will move to the next square B. And if it is not clean, then it will first clean A, then move to the next square B. So one very simple agent function is the following. If the current square is dirt, then suck, otherwise move to the other square. That is the vacuum cleaner world example. So here we can see what are the percept sequence. So first percept is A is clean. So the action will be right. So that means if A is clean, then it has to move to the next square B. Then another percept A is dirt. Okay, if A is dirt, then what will be the action? Then it will suck the dirt. So the action will be suck. Then B is clean. So B clean, then it has to move to the left. That means it has to move to A. Then B is dirt. Again suck. Then you can see the percept sequence. Initially A is clean and then again A is clean. Then also move right. A is clean, A is dirt, then the action will be suck. So you can see the percept sequence on the left side and the corresponding actions on the right side of this table. Next is rational agent. So what is a rational agent? A rational agent is one that does the right thing. Conceptually speaking, every entry in the table for the agent function is filled out correctly. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. So that means when we are considering an agent know has some prior knowledge about the environment that we can consider it as the built-in knowledge that is available in the knowledge base. And the sensor will collect information from the environment that will be the percept sequence. And the agent function that will find the better action based on this. And these actions that is expected to maximize its performance measure. So a performance measure is how we decide whether the agent is successful. For example, we can say that for a vacuum cleaner, cleanliness, low power usage will be the performance measure. For an intelligent agent, an agent that perceives and acts. That means collect information and accordingly they will act. A rational agent is an intelligent agent that acts optimally according to a defined performance measure. So we can say that all rational agents are intelligent agents, but not all intelligent agents are rational. Next, we will discuss about nature of the environment. How does an AI system decide what is the right action at a given moment? It depends on the nature of the environment and four important factors. So we will see what are the four factors. First one is performance measure that defines the criterion of success. Second one, agent's prior knowledge of the environment. And third one, actions that the agent can perform. And the fourth one, agent percept sequence to date. So for example, if you are considering a taxi driver or self-driving car, then we can see the performance measure. We can consider safety, speed, comfort, profit will be the performance measure. Then agent's prior knowledge that we can consider it as traffic rules, city maps. Then the action that the agent can perform that we can consider it as accelerate, brake, turn. Then agent's percept sequence to date. That means traffic signal changed from green to yellow, yellow to red. So we will see peace. What is peace? Performance, environment, actuators and sensors. So simply we can say that peace is used to describe the task environment of an agent. So when we are designing a agent or when we are designing an agent system, we have to consider these four factors: performance, environment, actuators and sensors. So here we will see a table. The table fully defines the task environment for a taxi agent. Here we can see taxi driver performance measure is safe, faster, legal, comfortable trip, maximize profit, etc. Then environment, roads, other traffic, pedestrians, customers. Then actuators means steering, accelerate, brake. Then sensors, camera, sonar, speedometer, GPS, etc. Then other examples we can see medical diagnosis system where performance measure is healthy patient and reduced cost. Environment is patient, hospital staff, and actuators means display of question, test, diagnosis, treatments, referrals, and sensors mean keyboard entry of symptoms, findings, patient's answers will be the some we can consider it as sensors. So other examples are given here. You can see satellite image analysis system. There the performance measure we can consider it as correct image categorization. That will be the performance measure. And the environment is downlink from orbiting satellite. And actuators, display of scene categorization, and sensors, color pixel arrays. Next is part picking robot. So here the performance is percentage of parts in correct bins. So the environment is conveyor belt with parts bins. Then actuators, joint arms and bat, and sensors, camera, joint angle sensors. Then refinery controller. There the performance measure is purity, yield safety. Then environment is refinery operators. Then actuators are valves, pumps, heaters and display, and the sensors, temperature, pressure and chemical sensors. Next example is interactive English tutor. There the performance measure is student score on test, and the environment is set of students, testing agency, and actuators is display of exercises, suggestions, corrections. Then the sensors, keyboard entry. Then next we can see agent programs. So agent program, that is a software that runs inside an agent. It takes percepts as input, the percepts as inputs, and produces actions as outputs. So here we can see a function, that is a table driven agent, decide what to do by looking up a table that maps every possible percept sequence into an action. So here we are considering a table driven agent as the function, and percept as the input, and the output is an action. So each time the agent receives a new percept, this function is called, and output is one action. So here the next line you can see, persistent means the data is remembered across function calls. So percept store all the percepts the agent has received so far. Initially the table is empty because the agent has not sensed anything yet. And here you can see that each entry will be added to the or appended to the table, and that is indexed by percept sequences. So agent remembers everything it has perceived so far. This forms the percept sequence. And agent searches the table, finds the action corresponding to the current percept sequence. So no thinking, only just looking in the table. That is only lookup. So then agent executes the selected action. The persistent percepts store the complete percept history, and the table maps each percept sequence to a predefined action. Next we will see type of agent programs. In artificial intelligence, agents are classified based on how they make decisions and act. So there are different types of agent programs. The first one is simple reflex agent. Second one, model based reflex agents. And the third one, goal based agents. Fourth one, utilities based agents. Then learning agent. And the last one is hybrid agent. We will discuss one by one in detail. First, we will discuss simple reflex agents. So these agents select actions on the basis of the current percept, ignoring the rest of the percept history. So that means it will not consider the history or percept sequence. It will only consider the current percept, and accordingly it will select the action. For example, a vacuum agent is a simple reflex agent because its decision is based only on the current location and on whether that location contains dirt. It is not checking the percept sequence. It is the vacuum cleaner world that only considers the current percept. Whether there is a dirt is there. If there is dirt is there, it will suck. Otherwise, it will check the location, and according to the location it will decide whether it has to move left or right. So here we can see the program, reflex vacuum agent. Their inputs are location and status, and it returns an action. So it will first check the status. If it is status is dirt, then return suck. Then the status is not there, then it will check the location. If location is A, then the action will be right. And if location is not A, it will check whether it is B. If it is B, then return left. Simple reflex behavior occur even in more complex environments. So we can consider an example, the driver of the automated car, taxi. So if the car in front brakes and its brake light come on, then you should notice this and initiate braking. So in other words, we can say that some processing is done on the visual input to establish the condition. We call the car in front is braking. So then this triggers some established connection in the agent program to the action initiate braking. So we call such a connection a condition action rule. So if a particular condition occurs, then a particular action should be taken. So that is condition action rule. So here the front car is applying brake. So the sensor perceives the environment and it collects that information that the front car brake light is on. So here we have to initiate the action, that is we have to apply the brake. So if car in front is braking, then initiate braking. That we can call it as condition action rule. So this is the architecture of the simple reflex agent. Here we can see the sensors that collect information from the environment. So what the world is like now. So that is the percent. And then it will check the agent program that will check the condition action rule. So condition is that will be depending upon the person and the corresponding action will be selected. So what action I should do now? So the particular action will be selected according to the person and the actuator will do or execute the corresponding action. So we will see the agent program. A simple reflex agent takes action based only on the current person using the condition action rules. So here we can see the function is called every time a new person arrives. So rules are stored permanently. So and this you can see that persistent here rules in a set of condition action rules. So then what the sensor is collecting information from the environment that we can consider it as a raw percept. So that should be converted into a particular format. So that is actually simplifies the sensor input. Then agent searches through the rules and find the first rule whose condition matches the current state, then extract the action part from the match rule. So there is no calculation or no planning. So then action is executed immediately. Second type of agent program is model-based reflex agents. The most effective way to handle partial observability is for the agent to keep track of the part of the world it can't see now. So the agent should maintain some sort of internal state that depends on the perceived history and thereby reflects at least some of the unobserved aspects of the current state. So that means here it will consider the current percepts. Along with that, it will consider the perceived history also. So accordingly, they will check the condition action rule and they will select the action. So, an example here we can see that. So, can a self-driving car rely only on what its sensors see at this particular moment? No, because the real world is partially observable and dynamic. So, this naturally introduces model-based reflex agents. So, we can say that a model-based reflex agent uses the current percept plus an internal model of the world to decide actions. So, internal model means we can consider the internal model in automatic taxi means automatic taxi maintains an internal state that represents aspects of the world not immediately visible. That includes road maps and lane structure, current position and speed, traffic signal states, positions and speed of nearby vehicles, pedestrian movement predictions, and traffic rules and constraints. So these are we can consider as the internal model. So not just what it sees now, that is we can consider it as internal, but also what it remembers and predicts. So why an automatic taxi is not a simple reflex agent? We can say that roads are dynamic. So sensors may be imperfect. Some information is not immediately visible. So a car ahead suddenly brakes. Pedestrian hidden behind another vehicle. So traffic signal just turned yellow. So we should then in these cases, so there we need the internal model. So automatic taxi operates in a partially observable and dynamic environment. So partially observable means cannot see everything at once. Dynamic means environment changes while agent is thinking. So here we can see that we already discussed everything. We will see taxi updates its internal states using previous state, current percepts from sensors, knowledge of how the world changes, knowledge of how action affect the world. For example, if a vehicle was observed in the blind spot a moment ago, a taxi assumes it may still be there. If brakes were applied, the taxi expects speed to decrease. So these we can consider as the internal state. Then for a reflex rule-based model, taxi uses condition action rules. So, but these rules are applied to the internal state, not just the raw percepts. In the previous case, we are only considering the current percept, but here we are considering the internal state also. For example, we can see if traffic light ahead is red, then apply brake. If vehicle detect a head slowing down, then reduce speed. If lane deviation detected, adjust steering. If obstacle predicted in path, change lane or stop. So these things we can include in the internal state. So these rules allow quick real-time reaction essential for safety. So road environment are partially observable. We already discussed this. Sensors have limited range. Objects can be hidden. Weather affects perception. So we are considering the internal state also. The internal model helps the taxi fill in missing information, making safer decisions. So this is the architecture of model-based reflex agents. Here we can see the sensors that will collect information from the environment, and here we can see there is a how the world evolves state and how the world evolves and what my action do. So that means that are the internal state. So we will consider the internal state along with the current percepts. Then the agent will check the condition action rule, and if a match is found, then the actuator will do or execute that particular action. Next, we can see the agent program for the model-based agents. So the agent program that receives a percept, that means the input from the environment, and updates its internal state. Then it will check the matching rules based on the updated state and chooses and return an action. So here we will see the line by line explanation of the code. The first is actually a function. This function takes the current percept and return an action. Then the persistent variables are state, model, rules, and action. State means agent's memory of the world. That means what it believes about the environment. And model means the knowledge of how the world changes, how actions affect the state. Then rules means condition action rules. And then action, that is the last action taken, and initially it is none. These are the persistent, meaning they are remembered across time steps. Next is update the state. So that means it uses the previous state, previous action, and current percept and model of the world and produce a new internal state. And this is the main difference from the simple reflex agents. Next is rule matching. So that means it finds the rule whose condition matches the current state. Next is selecting the action, that is execute the action specified by the matching rule. Then it returns an action. That means the chosen action is sent to the environment. So we can say that a model-based reflex agent maintains an internal state using a world model and selects action by applying condition action rule to the updated state. Next agent program is goal-based agents. So the agent needs some sort of goal information that describes situation that is desirable. For example, being at the passenger's destination. So we will see the example. How do you decide your route when you are going to college? You first think about where you want to reach. You choose actions that move you closer to that goal. That is exactly how a goal-based agent works. So agent asks, if I do this now, where will I end up? It compares different possible action sequences. For example, we will discuss taxi. If it turns left, there is a traffic jam is there. Go straight, then clear road. Then we will choose or agent choose straight road. The goal-based agent chooses actions by considering future consequences and selecting those that lead to closer to achieving its goal state. So search and planning are the subfields of AI devoted to finding action sequences that achieve the agent goals. So that means in goal-based agent, we will consider all possible solutions and we will choose one better action that led to closer to achieving the goal state. We can see the architecture of goal-based agent. Here, the input phase, that is sensors and percepts. The process start at the sensors. Sensors provide percepts, that means raw data, but raw data is incomplete. So the internal state, that is the core of this agent, and what is the world like now and how it works. So we will see how it works. The agent combines the new percept with its previous memory. So that means the internal state. This consists of two pieces of knowledge. One is evolution. That means how the world moves on its own. For example, we can say that if a ball is thrown, it will fall. So we already knows this. That is the built-in knowledge. Then action effects. What the agent's own action do. So that means if I turn the wheel, the car moves left. So if I do the action A, so what will be the result? Then the planning phase. This is what makes the agent goal-based. It doesn't have a set of if-then rules. It has a destination. The agent picks the action that brings it closer to the goal state. Then we have the output phase, that is actuators and actions. Once the best action is selected, it is sent to the actuators and the action changes the environment, which creates a new percept and the cycle repeats. Here, this is the detailed explanation. Agent perceives the environment, defines or recognizes a goal, evaluates all possible outcomes and their actions and their outcomes, then chooses the action that moves it closer to the goal and execute the corresponding action. Example, for a chess playing agent, the goal will be checkmate opponent. So what he will do, he will evaluate future board positions and chooses moves that increase chances of winning. That is the best example of goal-based agent. Next is utility-based agents. Reaching a goal is not always enough. How well we reach it also matters. So we can consider two routes reach the destination, route A and route B. Here the route A is long and safe and route B is short and risky. So both achieve the goal, but one is better. This leads to utility-based agents. We can see what is utility. Utility means actually a numerical measure of how desirable a particular state is to the agent. So higher utility means agent is happier, lower utility means agent is less satisfied. We can set the utility of each action. So if the safe plus and first route. That means our route A. So there we can set the utility as 90. Risky but fast. That means route B, we can set the utility as 60. So there will be a utility function. So utility function is essentially an internalization of the performance measure. So a more general performance measure should allow a comparison of different goal states according to exactly how happy they would make the agent. So an agent utility function is essentially an internalization of the performance measure. So performance measure, that is actually external. Utility function is internal, that is used by the agent, and the performance measure is actually given by the designer. So the agent converts the external goal into numeric score. So that means they will calculate some function, and they will calculate the function and they will get a value. So agent perceives the environment and predicts all possible future states, then calculate the utility of each state and select the action that maximizes the expected utility and execute the corresponding action. And here the maximizing utility means maximizing performance measure. So here we have already seen the example. There we have multiple routes. So evaluate the multiple routes, then chooses the one with the highest utility, not just the shortest path. A utility-based agent selects the action that maximizes expected utility, considering all possible outcomes and how desirable they are. It is not just reaching the goal, but choosing the best possible outcome. A goal-based agent only decides whether a goal is achieved or not. But in many cases, there are multiple acceptable outcomes will be there, and some outcomes are better than the other. Then the utility-based agent allow comparison between outcomes. So that means each action may lead to multiple possible outcomes, and each outcome has a utility value. That means how good it is, and there is a probability will be there. That means chance of occurrence. So agent chooses the action with the highest expected utility. So here the limitations of the goal-based agent that can be overcome using this utility-based agent. That means in the goal-based agent, we are checking whether the goal achieving or not. But in a real-time environment, many outcomes can reach the goal. Some outcomes are better than the other. So that means if you are considering an example, reaching a destination. The first case, in 20 minutes we will reach. That is the better solution. In another case, in 40 minutes we will reach. That is acceptable. And the third case, in 1 hour we will reach. So that is poor. So goal-based agent treats all these cases equally, but in the utility-based agent compares the quality. Then if you are considering another example, self-driving car, there will be different routes. All routes may leads to the destination, but we can consider different factors like safety, time, comfort, fuel efficiency and all. And the utility-based case agent, it evaluates all the routes and computes the expected utility and chooses the best overall option. Next, we will see the architecture of utility-based agent. Here also the sensors collects percept from the environment, and these percepts describe the current situation. Next, we have internal state that represents agent's current understanding of the world. That may include information not directly observable. Then model of the world. That includes how the world evolves. That means describe how the environment changes on its own. We already discussed in the previous case. For example, traffic lights change, other vehicle move. Then what my action do? That describes how agents' actions affect the world. For example, accelerating increase speed, turning that means car turns that changes the direction. Next is actually prediction. What it will be like if I do action A. So agent simulates future states. For each possible action that predicts what will be the resulting state. For example, if I take route A, I will reach in 30 minutes. If I take route B, I will reach in 40 minutes. So here I will consider the utility function. How happy I will be in such a state. Assigns a numerical value to each possible state and measure how desirable a state is. For example, in the case of a taxi, we are considering the utility factors, safety, time, comfort, and fuel efficiency. So higher utility means better outcome. So next is decision making. So there, what action I should do now. So agent calculates expected utility for each action and chooses the action with the maximum expected utility. This is the core of the this utility based agent. And then we have actuators execute the selected action in the environment. The environment changes and the cycle repeats. Next, we will see this is the explanation of the utility-based agents we already discussed. That is, the agent perceives the environment, generates all possible outcome actions, and predicts outcomes of each action, calculates the utility value for each outcome, and select action with the maximum utility. For example, medical diagnosis system, utilities assigned to treatment, success, risk and cost. So these are the performance measure we have considered: treatment success, risk and cost, and utility value also assigned to all these cases. Then chooses the treatment with the maximum patient benefit. Next is learning agent. A learning agent is an intelligent agent that improves its performance over time by learning from experience and feedback from the environment. Human beings are the classic examples of learning agents. Here we can see the architecture of the learning agent. There are four main blocks: performance element, critic, learning agent, and problem generator. We will discuss one by one. First, we will see performance element. It selects action based on the current percepts, and it is directly interacting with the environment. It takes the input from the sensors. Here in the figure we can see that the sensor collects information from the environment, and this is the input to the performance element. And it chooses actions through the actuators. For example, in a self-driving car, steering, braking, accelerating. So this part is responsible for current behavior. The next block is critic, that evaluates how well the agent is performing. There are two inputs to the critic. First one is percept from sensors, and the second one is performance standard. And the output will be feedback to the learning element. So for example, it tells the agent, your last decision reduces fuel efficiency. The critic does not decide action, it only judges performance. Next is learning element that improves the agent's behavior over time, uses feedback from the critic and modifies the knowledge of the performance element. For example, update the rules or models, learn better strategies. So this component is responsible for learning and improvement. And the next one is problem generator that suggests new actions or exploratory behaviors. If the agent only exploits known actions, learning stops. Exploration helps discover better strategies. For example, trying a new route instead of the usual one. Then interaction with the environment, sensor receive pulses from the environment and actuators that execute action chosen by the performance element. So we already discussed these four components of the learning. The working of a learning agent we already discussed, and we will just go through it. Agent perceives the environment, performance element select an action, action is executed, critic evaluates the result, and learning element updates knowledge, and problem generator explores new actions. We will see the example learning agent in automatic taxi. We will see in detail in the next slide. In this slide, we will discuss about the four components of learning agent using an example automated taxi. So we will see each components. First one is performance element. That means what the taxi does. The performance element contains, in this case, driving rules, traffic laws, navigation algorithms, control procedures like steering, applying brake, accelerating, etc. So, selecting a driving action such as turning left or right, accelerating, braking, changing lanes are done by this performance element. The taxi drives on the road using its current knowledge. So, this part acts directly in the environment. And the second component is critic, who judges the taxi. So, the critic observes the taxi's behavior and environment's response. What it will check? It will check safety, passengers' comfort, traffic rule violations, reactions from other drivers, etc. So, we are considering an example. After the taxi makes a dangerous quick left turn across three lanes, then the critic will conclude this action was bad. So, next we will consider the next component, learning element, who improves the taxi. The learning element uses feedback from the critic and learns that the action was unsafe. So, in the previous example, from the feedback from the critic, the learning element formulates a new rule: avoid sharp multi-lane turns in heavy traffic. So it updates the performance element by installing the new rule. So the taxi does not repeat the mistake in future. And the fourth component, problem generator, who encourages experimentation. The problem generator suggests new experiments to improve behavior. So testing braking behavior on wet roads, muddy roads, high-speed highways. These are the examples. So that helps the taxi learn faster and safer. Next is hybrid agent. Hybrid agent is an intelligent agent that combines two or more agent architectures, such as reflex, model-based, goal-based, utility-based, and learning agent to achieve better performance, flexibility, and adaptability. An automated taxi is a classic example of a hybrid agent. It uses reflex behavior to brake immediately when an obstacle appears, a model-based approach to track nearby vehicles and traffic conditions, and a goal-based strategy to reach the passenger's destination, and a utility-based method to choose the safest and fastest route, and learning capabilities to improve by understanding traffic patterns and user preferences over time. And the next one is problem solving agent, that is similar to goal based agent, and we will discuss this problem solving agent in detail in the next week. Thank you.